It's been, I think, about 10 years since I actually was last at an ICMOVPE conference. So it's a pleasure to, in a way, be back amongst you growers who we all know are at the heart of 3.5 materials and devices. And it's a special pleasure to be able to talk about a new technology that might very well be the killer app in 3.5 EPI, solid-state lighting. Now, many of you already know a lot about the story of solid-state lighting. One way I like to think about the story of solid-state lighting is as a story of stepping stone markets. You penetrate a small market first that doesn't require a technology with very high performance. And you use that revenue to invest in R&D to improve your technology so that you can successively penetrate bigger markets that require successively better performance. And for colored LEDs, I show some of those stepping stone applications here. Some of you are too young to remember some of these. The handheld calculator was probably the first important one. Then there's the center high mount stoplight, the so-called chimsel. Then there's traffic lights, of course, large outdoor video displays. And for white LEDs, some of the important stepping stone markets are indicated down here. Flashlights, of course, flashes and backlights for mobile appliances like digital cameras and cell phones. And then, of course, most recently, the backlights for larger liquid crystal displays like computer monitors and televisions. And as many of you know, this application is so big that it's causing a worldwide shortage of LEDs right now and a worldwide boom in MOVPE reactor sales right now. In fact, all of these stepping stone applications depended on some feature like lifetime, reliability, compactness, efficiency that was unique to LEDs so that LEDs could penetrate these markets even though the raw economic cost of LEDs in these applications, at least at first, was not lower than that for traditional fluorescent or incandescent lamps. So the result has been a steady increase in manufacturing volume, a steady improvement in performance, a steady decrease in price as LEDs penetrated these markets. So the end game of all this, of course, is when solid-state lighting penetrates the market for general illumination. And when it does so, the world will be a very different place. Every lamp on Earth is potentially an LED, all the way from your smallest signal lamp all the way to your largest stadium scale flood lamp will be an LED. And the amount of light, the amount of artificial light that the world consumes is very likely to be vastly bigger, vastly larger than the amount of light that we consume right now. So what I'd like to do in this talk is a couple of things. First thing I'd like to do is to speculate a little bit about what this world might look like in the end game when solid-state lighting has penetrated fully the market for general illumination. And the second thing I'd like to do is talk about some of the economic and technical challenges that we face as a community en route to that end game. Okay, and just a quick comment before I start. I do tend to go pretty slowly on my view graphs, so if it looks like I'm running out of time, don't worry. I actually don't have very many view graphs. Okay, so let's start with the end game. And to try to understand that end game, let me start by putting that in a bit of an economic perspective. Let's talk about the history of the consumption of light so that we can use that history to project into the future, into that end game. So here I show a plot of the consumption of light for a number of nations and groups of nations at various stages of technological development. Down here in the lower left, for example, you see the United Kingdom in 1700 when candles were the dominant lighting technology. A little further along in time, you see the United Kingdom in 1850 where the dominant lighting technology was gas and kerosene lamps. Then there's a whole cluster of data points from the more contemporary world on grid electricity, where, of course, electric lighting is now the dominant lighting technology, high-intensity discharge, fluorescent, and incandescent lamps. The vertical axis of this plot is consumption of light, phi, with the units petalumen hours per year. So this is a very big unit of light. The horizontal axis of this plot is this funny expression. It's beta, just a fixed factor, times the ratio between gross domestic product, GDP, and the cost of light, COL. And if you use as your units for GDP, gigadollars per year, that's billions of dollars per year. And if you use as your units for cost of light, dollars per megalumen hour, what you see is that this ratio has exactly the same units, petalumen hours per year, as the vertical axis does. Okay, and if you choose as your constant for this beta constant, if you choose 0.0072, what you find, amazingly, is that these empirical data points fall roughly on a line of slope 1. Okay, so this has two implications. Okay, one implication is that as GDP increases, the consumption of light increases linearly. That is to say, the wealthier we are, the more light we consume. Okay, the second implication is that as cost of light decreases, also consumption of light increases. So the cheaper, again, linearly. So the cheaper light is, again, the more light we consume. Okay, so to put this in a little bit of perspective, here on the right, I've called out a few data points from the contemporary world. And in this table, I show a few quantities. One is the cost of light, which is approximately equal to the cost of energy that you're using to produce light, divided by luminous efficacy, lumens per watt. I also show gross domestic product, which is just equal to population times per capita GDP, per capita gross domestic product. And then I show consumption of light phi, as well as per capita consumption of light. It's sort of lowercase phi. It's supposed to be a lowercase phi. Okay, so the first data point I'd like to call your attention to lies at one extreme of the contemporary world. That's this row down here, the undeveloped world not on grid electricity. Okay, that's this green data point right here. Okay, the undeveloped world not on grid electricity. As you can see, it doesn't consume much light. On this scale, it's sort of like it's like 1/20th of a petalumen hour per year. Okay, that's about a factor of 2,000 less than the contemporary world in 2005. Okay, so there's two reasons for this. One reason is that, of course, this world is very poor. It has a per capita GDP of on the order of $2,200 per person year. So even though it has a lot of people, 2 billion people, so that's about a third of the global population, still its total gross domestic product is relatively low, $4 trillion per year, as opposed to $60 trillion for the world as a whole. Okay, so that's one reason. But the most important reason why this world doesn't consume much light is because its lighting technology is based on kerosene lamps. And kerosene lamps, as you may know, has a very, very low luminous efficacy, about a third of a lumen per watt. And because of this very low luminous efficacy, the cost of light in this world is extremely high, $600 per megalumen hour, compared to $3.3 per megalumen hour for the rest of the world. So this ratio, GDP over cost of light, is very small for this undeveloped world. GDP is low, cost of light is very high, and so the consequence is that this undeveloped world consumes very little light. Okay, the second data point I'd like to call your attention to lies at the other extreme of the contemporary world. That's the US in 2001. Okay, that's this blue data point up here. The US consumes a ton of light. Something like 40 petalumen hours per year. That's about a third of the entire world consumption of light. And of course, it has the same two reasons, except in the opposite direction as the undeveloped world. The US is rich. So, of course, it has a very high gross domestic product. Surprisingly, interestingly, the U.S. also has a relatively low cost of energy. Some of you may know that. So it's about $76 per megawatt hour as opposed to the world's $120 per megawatt hour. So that translates into a cost of light, which is lower, $2 per megalumen hour as opposed to the world's $3.3 per megalumen hour. So those two factors combined conspire to enable the U.S. to consume a ton of light. In fact, one could argue that the U.S. is really the lighting hog of the world. This translates in terms of per capita units to a U.S. consumption of light of 136 megalumen hours per person year, compared to 20 megalumen hours per person year for the rest of the world. And 136, to put that in perspective, 136 megalumen hours per person year corresponds to the average person in the U.S. being surrounded during his or her waking hours by 17 100-watt incandescent light bulbs. So that's a huge amount of light. Of course, that doesn't mean that we're all literally at every moment surrounded, but in factories and offices and whatever. So the U.S. is really a very, very big consumer of light. Okay, the third data point I'd like to call your attention to is this world in 2005. That's this point up here. This is just the total integrated light consumed by the entire world. And so, of course, that is a big number. That's about 130 petalumen hours per year. Okay, so this is what lighting has done in the past. This is sort of the historical record of consumption of light over the past 200-300 years or so. So let's maybe suspend judgment. Let's assume that that might happen in the future, that this historical dependence on beta times GDP divided by cost of light holds in the future. Now, we don't know that that will be the case, of course. That's predicting the future. And in fact, there are many reasons that one can think of for why light consumption might not do that in the future. Nevertheless, this is sort of a reasonable baseline guess that the future might be similar to the past. And if one were to predict that the future is not going to be like the past, then you would have to come up with some good arguments for why it might not. So this is sort of a baseline assumption that the future is going to look like the past. And so let's suppose in the end game, 20 years from now, maybe more, but let's say 20 years from now, we have reached some sort of end game. Solid-state lighting has penetrated the market for general illumination. It is the dominant lighting technology. And suppose we've reached at that point some tremendous efficiency. Let's say a wall plug efficiency of 70%, which is not unreasonable. The best optoelectronic devices now are on the order of 75, 76% efficiency. That translates to a luminous efficacy of about 270 lumens per watt. Okay, so let's assume we can get there. Let's also assume EIA, the U.S. Energy Information Agency, projections for world GDP, 140 in the year 2030, $140 trillion per year. And let's assume EIA, again, projections for the cost of energy in 2030 of about $120 per megawatt hour. And if you make those assumptions on luminous efficacy, on cost of energy, and on gross domestic product, what you end up with is a consumption of light for the world in 2030 of about 1,700 petalumen hours per year. Okay, so this is a tremendous amount of light. On this plot, actually, so that's this white diamond outlined in purple in the upper right of that plot. And actually, on this plot, it doesn't really look like it's much bigger than the world in 2005. But notice that this is a log plot with 2 orders of magnitude per grid spacing. So this is more than a factor of 10 more light than we are consuming right now, 1,700 petalumen hours per year, as opposed to 130 petalumen hours per year. So this is a tremendous amount of light. Imagine if in this satellite world at night photo, taking this photo 20 years from now when we are consuming more than 10 times more light than we are now. So there's more than 10 times more light leaking out into the night sky. Okay, so that's a possible consumption of light scenario in the distant future when solid-state lighting has reached its end game. So let's call that the demand for light. And I've written it up here on the left, that exact same equation. It's this beta factor, just a fixed constant times GDP divided by cost of light. But now I've rewritten the cost of light as the cost of, as approximately as the cost of energy divided by the luminous efficacy. Okay, so this is the demand side, I guess, of the equation for consumption of light. Again, we're supposing that solid-state lights have penetrated totally the market for general illumination. So they are the technology that's supplying all this light. And if we know the operating costs of the semiconductor chips that are being used to produce that light, then we can write down an equation for how much light those semiconductor chips will be producing. Let's call that the supply of light. And let's write it down as the product of four factors. There's the input power density into the chip. There's the area of the chip. And these two factors together, P times A, that's just the total power into the chip. Then, of course, there's luminous efficacy. That's how many lumens you get out of the chip for a given amount of input power into the chip. And then there's the duty cycle. Maybe the chips aren't on all the time, but only some fraction of the time. And so now we can equate these two things, demand and supply, and we can solve for the area of the semiconductor chips that are required to light the world. So that's shown down here on the lower left. And you'll notice that this equation doesn't have luminous efficacy in it. And when I first saw this, I thought that's actually quite weird. But the reason is that luminous efficacy appears in both the demand and the supply side of these equations. If luminous efficacy increases, the cost of light, which is COE divided by luminous efficacy, decreases. And if COL decreases, then then light gets cheaper and the consumption of light increases, demand for light increases. But at the same time, if luminous efficacy increases, the area that you require to produce that amount of light decreases. So these two factors of luminous efficacy exactly cancel each other, and so they don't appear at all in the equation for how much area you need in order to light the world. So now, of course, if we want to estimate this area, which would be nice to do, we have to make some guesses. We have to make some estimates of what these various factors are. And that's non-trivial, but again, let's make some guesses. And let's use the same factor beta that we used before. Let's assume EIA projections for GDP in 2030. That's $137 trillion per year. EIA projections for the cost of energy, say $120 per megawatt hour. Let's assume an input power density that corresponds to, let's say, 1 amp into a 1 square millimeter chip. That's not too far off from what we're doing now in industry. And let's assume something like 3 volt bias. So that gives us something like 300 watts per square centimeter. And let's assume a duty cycle of 1/4. That would correspond to your lights being on for 6 hours every day. And that's roughly what holds for traditional lights right now. And if you plug in all these numbers, what you end up with is that the area in steady state, the area in the end game, the area required to light the world is something like 1.3 square kilometers. Okay, so this is a huge area. This corresponds to, it doesn't look like such a huge area when you express it in square kilometers, but if you express it as numbers of American football fields, it's something like 240 American football fields. So that's a huge amount of area that one would need in order to light the world. Okay, so now with this estimate, now we can go on to estimate other things which are also of interest, such as the area turnover. So of course these solid-state lighting chips will have a lifetime. And so every year you will need to manufacture some chips to replace the ones that burnt out. So this is the steady state area turnover that you might need. And let's write that as dA dt. So this is the manufactured volume or manufactured area of chips that you would need in order to sustain this end game. And that's just equal to the area that you need to light the world divided by the lifetime. of those chips. But of course, the chips aren't on all the time, so you have to normalize the lifetime by the duty cycle. And not every chip that you make will be a good chip, so you have to normalize that area by the yield. And again, you have to make a lot of assumptions, and that's non-trivial. But let's take some guesses. In the spirit of speculating on what the world might look like in 2030, let's take some guesses. Let's assume a lifetime of the chip that's something like 25,000 hours, which is on the order of what the current sort of generation of solid-state lighting replacement lamps for incandescent is doing. Let's assume a duty cycle of 1/4, just like we had assumed before. And let's assume a yield of, okay, in the end game, where yields are getting pretty high because the manufacturers have really have their manufacturing processes well honed. Let's assume a yield of, say, on the order of 3/4. And if you plug in all of these numbers, what you end up with is an area turnover that's something like 0.15 square kilometers per year. Again, that actually expressed as square kilometers, that seems like a small number, but that's 28 American football fields per year. So at least on my scale, that's a very big area. Okay, so then we can go on to estimate another quantity that might be of interest to a lot of the MOVPE reactor manufacturers in the audience. How many MOVPE reactors might you need in order to sustain this kind of area turnover, which in turn is necessary to sustain this steady state area required to light the world? And so here, that number, I've expressed it as the area turnover itself, dA dt, divided by a bunch of factors. Let's assume we're dealing with 4-inch wafers. Maybe the wafers will get bigger. There's numbers of wafers per run, number of runs per day, uptime of the reactor. And again, we've got to make a bunch of assumptions. And again, that's non-trivial, but again, let's make some guesses. And let's assume something like 12 wafers per run, maybe 3 runs per day. So these reactors are running around the clock. They get no rest. And let's say an uptime of maybe 330 days per year. So they're up most of the time. And again, if you plug in all of these numbers, you come up with an estimate of something like 800 of these sort of big scale, production scale MOVPE reactors that you would need in order to sustain this area turnover, which in turn is necessary to sustain the area required to light the world. So this, I don't know exactly what the numbers are of this sort of scale reactors that are in the field right now for gallium nitride based applications, but I think it's on that order. It's so what we're talking about is in the end game requiring a doubling of the number of reactors that are perhaps present right now in order to sustain this kind of general illumination market. Now, I want to emphasize this. This is speculation. These are estimates only, and they depend on a whole bunch of assumptions, not the least of which is that the demand for lighting will follow what it has followed in the past. We have no idea what will happen in the future. But nevertheless, it perhaps is useful because it sort of frames the order of magnitude of the manufacturing issues that we face. It's probably not a factor of 10 more reactors that we'll need in the year 2030, but it's also not 10% more reactors. It is a lot more reactors that we would need. Okay, so to put that all in a larger perspective, here I've called out a bunch of other killer apps in the electronics arena. I don't know if this is all of them that are really big, but I think they are most of them anyway. So again, just to put solid-state lighting in a perspective, here are some of the really big ones. Liquid crystal displays, as you all know, is a huge one, and it's growing incredibly quickly with a bunch of different markets, whether it's cell phone displays or computer monitors or televisions. And last year, an estimate for not the area turnover, the manufactured area in this case, the manufactured area in 2009 was 230 square kilometers per year. So this is a really gigantic number. This corresponds to 43,000 football fields per year. And it's about half the size of the city that we're in right now, Lake Tahoe. So this is, an enormous amount of area that liquid crystal displays are consuming. The second application I show here, second market I show here is solar cells. And this market, of course, is also growing very fast, split between various technologies like crystalline silicon, amorphous silicon, thin film technologies. And last year, sort of a guess for the approximate area turnover is something like 60 or so square kilometers per year. So not as much as liquid crystal displays, but still a very big number. And that corresponds to 11,800 football fields per year. So that's the size of Manhattan. So that's a big number all by itself. Okay, then the third application, or third market is silicon electronics, integrated circuits, transistors. And that market, as many of you know, had a sort of a down year, 2009, just like the rest of the world economy had kind of a down year last year. But still, it had an approximate area turnover or manufactured area of about 4.4 square kilometers per year. And that corresponds to 800 football fields or twice the size of the country of Monaco. Okay, so on this scale, solid-state lighting actually looks kind of puny. 0.15 square kilometers per year compared to 230 square kilometers. So it actually looks, kind of small. But remember, this is still 28 football fields per year. So this is still very, very big. I mean, this is about 1/4 the size of Vatican City. And the estimates I was able to come up with, but I'd be interested in better estimates, it's still about a factor 4, maybe 5 bigger than the chip area manufactured for gallium arsenide electronics, which is maybe about 5 football fields. Also still a pretty big number, but now, so what this says is that solid-state lighting will not be the biggest market for square kilometers of area in electronic thin film applications. Those honors certainly will go to liquid crystal displays, solar cells, silicon electronics. Nevertheless, it could very well be the killer app in 3.5 materials and devices. Of course, we don't know how gallium arsenide electronics or other gallium arsenide-based markets like concentrating photovoltaics, we don't know how they will evolve between 2009 and 2030. So it would be maybe foolhardy to say definitively that solid-state lighting will be the killer app, but it could be the killer app. It's certainly within the realm of possibility. Okay, so let's see. So up until now, I've talked exclusively about the end game, what might happen in the distant future when solid-state lighting really has come to dominate general illumination. Of course, we're nowhere near that end game yet, and there are all sorts of challenges that we face en route to that end game. So in the next couple of views, let me just talk a little bit about those challenges, and let me start by putting those challenges in an economic perspective. And in order to do that, here I've drawn on the left plot basically the two important costs associated with lighting. Okay, not just solid-state lighting, but lighting in general. The first cost is on this vertical axis is the capital cost of light. It's basically the cost of the lamp that you buy, amortized over the life of the lamp. So that's the capital cost of the light. And then on the bottom axis here, the horizontal axis, is the operating cost of light. That's basically the cost of electricity, the cost of energy, divided by the luminous efficacy. So you're just paying for electricity, basically, to convert that into light. Both of these costs have the same units, dollars per megalumen hour, and the sum of those costs is what one would call the ownership cost of light. Okay, here on this plot also I show a bunch of circles, colored circles in red, blue, and green, which correspond to traditional lamps. The red circles, open circles, correspond to incandescent lamps. The blue open circles correspond to fluorescent lamps. And the green open circles correspond to high-intensity discharge lamps. And the sizes of all of those circles correspond to the market size of those lamps. The lines that are drawn through, the curves that are drawn through, the colored curves, the red, blue, and green colored curves that are drawn through those points represent contours of constant ownership cost. So any point that lies along one of these contours corresponds to the same ownership cost, even though it might correspond to a different division between operating and capital costs. And one of the things that you'll notice that I would like to call your attention to is that most of these data points seem to fall along a line which has a ratio 1:6. That is to say, a line along which the capital cost of light is about 1/6 the operating cost of light. So that just says what we, I think, already intuitively know, and that is that when you use a lamp, the dominant cost of that lamp is really the electricity. It wasn't the purchase cost of the lamp that you purchased from Home Depot. And that's in the ratio about 1:6. So this 1:6 line is just a line of slope 1 offset downwards on this log plot by a factor of 6. Okay, so what does this, so on this plot, how does solid state lighting look? So here in the tan points with white circles around them, I draw the last 5 years of progress in solid state lighting. And what you see is that there's been progress vertically downwards on this plot, as well as progress that one might think of as being diagonally down and to the left on this plot. And I like to show it that way, and the reason is as follows. If you rewrite the capital cost of light in this peculiar way, it's a little bit unconventional, but I like doing it this way, as the cost of a lamp that sinks a certain amount of power. So I call that dollars per watt in, and that has the units dollars per watt. Okay. Divided by the luminous efficacy, and then all amortized over the lifetime of the lamp, Tau. I like doing it this way because you separate out improvements in luminous efficacy from improvements in manufacturing cost. So if you write it this way, what you see is that if you decrease your cost of a lamp that can sink a certain amount of power, then you move vertically down on this plot, exactly vertically down. Okay. Whereas if you increase luminous efficacy, luminous efficacy appears in the denominator of both the capital cost of light and in the denominator of the operating cost of light. So if you increase your luminous efficacy, then you move diagonally downwards and to the left on this plot. And so what this shows is that one can think of the last 5 years of progress as being in 2 dimensions. One dimension has been a decrease in cost, the cost of a lamp that sinks a certain amount of power, dollars per watt in, by a factor 7.1x, approximately. And that's moved one vertically downwards on this plot. At the same time, there's been an improvement in luminous efficacy by 3.5x, which moves one diagonally downwards and to the left, and improves both the capital cost, decreases both the capital cost and the operating cost of light. So the bigger improvement over the last 5 years has been in this the cost of a package that sinks a certain amount of power. It has not been in luminous efficacy. Not that there hasn't been good progress in luminous efficacy. Okay, so now what does this say about the future? Well, one can imagine similar things will happen in the future. One can imagine that there will be continued pressure on luminous efficacy to increase. And so here on the right, I show some hypothetical trajectories that solid-state lighting might obey in the future, or might follow in the future. And so luminous efficacy, in fact, if you increase luminous efficacy by a factor of 4.6, then what you end up with is you follow this, again, diagonally downwards and to the left path, and you end up at a luminous efficacy that's about 270 lumens per watt, which is about that 70% wall plug efficiency that we sort of assumed in the earlier view graphs. So 4.6x gets you to the end game, basically. At the same time, of course, there will be continued pressure on cost. And in fact, if you decrease cost by something like 4.9x, these factors are very similar, you end up moving downwards, vertically downwards, to the point where you exactly meet that 1:6 cost structure line Okay, once you've reached that 1 to 6 cost structure line, there actually isn't much point in decreasing your manufacturing cost much more, because at that point, lighting is dominated by the operating cost and not by the purchase cost. And so there will be all sorts of incentive, I think, for manufacturers not to go much below this 1 to 6 line. Of course, progress isn't going to be a serial process, as I sort of hypothetically drawn here in this white dashed line. It's got to be sort of in parallel. And so here I've drawn again, very hypothetical black dashed line for a hypothetical trajectory for how solid-state lighting might evolve. And it's weighted initially towards luminous efficacy, in part because one can see in research labs all over the world tremendous progress in luminous efficacy over this past year, and you know that that's going to translate into manufactured product before too long. So it's weighted initially towards luminous efficacy, but we know cost has got to catch up. And at some point, in fact, I've drawn here this very hypothetical scenario, cost might even overshoot. One could imagine that cost could overshoot. We know that semiconductor industries hate this, but they're plagued by it. You end up with these boom-bust cycles. You end up with price wars. You end up with all sorts of, terrible things for the industry, but maybe good for the consumer. Who knows? So it's not entirely impossible that one end up in some sort of price where it actually overshoots, and the cost of these solid-state lamps actually goes below this 1 to 6 cost structure line. At that point, though, and maybe even well before that point, again, there will be all sorts of incentives for manufacturers to not do that. And one way in which they can avoid doing that is to add more functionality. Instead of having lamps, which right now are just pretty dumb, you have factory preset color points for and color temperatures for your white lamps. Instead of having that, you could go to smart lamps, where now you have in-the-field tunable color points, in-the-field tunable white lamps. And by adding functionality, one could hopefully increase the cost. Maybe not go much above the 1 to 6 line, but who knows? Maybe it could be above the 1 to 6 line. But to add functionality so that so that manufacturers can stave off commoditization, at least temporarily stave off commoditization, and then finally reach this sort of, in a way, end game where you're on this 1 to 6 cost structure line, and you've reached a luminous efficacy that's extremely high. So luminous efficacy, cost, functionality, maybe not quite in that order, but those are the three sort of, in a way, sort of economic drivers that I can see for solid-state lighting. Okay, so let me now translate that into technology challenges, those economic trajectories into technology challenges. And here I list 3 that one might call grand challenges. Doesn't mean that there aren't a lot of other challenges that are also very important. But here I just call out these 3, aimed respectively at different aspects of those economic trajectories: luminous efficacy, cost, and functionality. And let me just spend a few minutes going through these. The first one is luminous efficacy, and I call it narrow line width, shallow red color conversion. And to see why that's important, here I draw 2 spectra. The spectrum on the upper spectrum is the human eye response, basically just lumens per watt that the human eye sees as a function of wavelength. And in the bottom spectrum, I show a spectrum of a state-of-the-art LED. These dashed vertical colored lines correspond to the wavelengths that best optimize luminous efficacy and color rendering for an RYGB white light source. Okay, so one thing you'll notice is that this red wavelength isn't very red, actually. 614 nanometers is actually almost orange, sort of a very, very shallow red. So it's not a very deep red at all. Okay, so now in this bottom spectrum is a state-of-the-art LED. You can see it has 3 humps. There's a hump in the blue, that's the blue LED. There's a hump in the green, a fat hump in the green that's due to the green phosphor that absorbs in the blue, re-emits in the green. There's a hump in the red, which I've called out in this sort of dashed red line, which is the red phosphor, which absorbs in the blue, re-emits in the red. And you can see that it's pretty fat. And in fact, it's so fat that it spills over significantly into the deep red, well beyond this 614 nanometer optimal red wavelength that optimizes, again, luminous efficacy and color rendering for a white LED. So the challenge here is to replace this phosphor with another kind of phosphor or some other kind of color converter that is centered at 614 nanometers, centered in this shallow orange-red, but doesn't have the spillover into the deep red where the human eye isn't very sensitive. Okay, so that's one challenge aimed at luminous efficacy. Second challenge aimed at cost more than anything else is, I think, a challenge that I think you in the audience are very familiar with, is to eliminate blue LED efficiency droop. And this is important for cost, of course, because if you can drive your chip twice as hard without incurring much of an efficiency loss, and also without incurring much of a packaging cost, because, of course, to package a chip that sinks twice more current can be more expensive. But if you can do that without incurring too much more cost, then you've basically halved your capital cost of light. So this is a big deal for cost. Now, I think this is a very, very, very active area right now. As far as I can tell, nobody really knows what the origin of blue LED efficiency droop is. Perhaps it's some CN cube, some Auger kind of term. Perhaps it's some sort of injection inefficiency that kicks in at high currents. We know that resistive losses at some point are going to kick in as well in terms of rollover inefficiency as a function of current density. I list here as sort of a target. If one could get to 200 amps per square centimeter, one could get very close, not quite, but very close to that 1 to 6 cost structure line. So 200 amps per square centimeter is a kind of a nice target. Okay, then the third grand challenge aimed sort of both at luminous efficacy and functionality is to fill in this red, yellow, green, this famous red, yellow, green gap, ideally with electroluminescent semiconductors, and perhaps to add control loops. And of course, this is important because if you can really get semiconductor electroluminescence, then you can eliminate the Stokes shift associated with phosphors. You can increase your luminous efficacy right away. Also, if you can have independently controlled semiconductor lamps, and if you can add control loops, then you can add that kind of functionality that I talked about earlier. You can make your dumb lights become smart. And I think in the long run, that's going to be very, very, very important. Of course, this is a big challenge. InGaN, as we know, is good in the blue, getting better in the green, but not very good in the yellow and red. Allen gap is good in the deep red, but not very good in the shallow orange-red. Definitely not very good in the yellow. Okay, so with that, let me close by just saying that we are in an incredibly exciting time now. I think we all know. We stand at the brink of a revolution in lighting when every lamp on Earth is going to be a solid-state lamp. I have no doubt. I think that that's going to happen. How it happens is maybe another question, but it will definitely happen. We have to have some humility. We will not be the biggest killer app in electronics, at least in terms of area. But we may be the killer app in 3.5 materials and devices. And finally, let me just acknowledge some coworkers who have contributed a lot to my thinking and to this talk. Randy Creighton, Mike Coltrane, Roland Heitz, Harry Saunders, Eric Shaner, Jerry Simmons, Paul Wade, and let me especially acknowledge the Department of Energy Office of Basic Energy Sciences for their support through their Energy Frontier Research Center for Solid-State Lighting Science. And thank you very much.
Thanks, Jeff, for this illuminating talk. We have time for a few questions. Dan?
Jeff, I have two questions. One is you didn't factor in potential competitors, such as OLEDs, which will impact both the lighting market as well as the display market. And secondly, you didn't seem to include the volume that would be contributed by the display market into lighting. Can you comment on those two?
Yes. Well, okay, so the question is, what about OLED? Well, two questions. First question is, what about OLEDs? Why didn't I even talk about OLEDs? And yes, OLEDs would be a very different creature. OLEDs, of course, are a little bit further back in maturity and all of that. Who knows whether, but they could very well be viable competitors in the future. But I think it's mostly because of my ignorance that I didn't really discuss in detail the OLEDs. Of course, that's a very different proposition as well. The cost structure is totally different. Now we're talking about huge areas as opposed to maybe smaller point sources. But yeah, so it's my ignorance. Second question is, what about the market for liquid crystal displays? Of course, that's a huge area, and associated with that huge area are LEDs that backlight the LCD displays. And is that market going to be maybe as big or bigger than the market for general illumination? And actually, it's only as I started preparing for this talk and I saw that number of 230 square kilometers for the liquid crystal displays, and I started reading up a little bit on the strategic plans of some of these big LCD companies where, they're talking about art walls where, the entire wall will be an LCD. It's only when I started to realize that it occurred to me that, oh my goodness, maybe general illumination, which has been near and dear to a lot of people's hearts over the past 10 years, who knows, maybe, and so I think that's definitely something that's worth delving into. It is not, I think, out of the realm of possibility that be, and you can imagine even these art walls, they will supply some degree of dim illumination, or maybe illumination for the room as well, not just be supplying images. So yeah, that's a very good question, Dan.
Tony?
Yes, Jeff. Have you considered the increase in the power generation that's going to be needed to meet your 2030 projection? If everybody on the planet is going to be using the same amount of illumination.
So the question is, what about electricity consumption? And what's interesting about this is that if the future is like the past, electricity consumption actually, electricity consumption as a percent of GDP actually ends up being sort of the same. So what this is saying is that we're not necessarily going to save energy. So the promise of solid-state lighting has for a long time been that for some reason we are saturated in terms of our consumption of light. Okay, so if we come in with a lighting technology that's more efficient and we consume the same amount of light, then, well, of course, we're going to save some energy because we're not going to be needing as much energy to produce the same amount of light. So I think what this is saying is that if the future is like the past, then in fact, we're probably going to consume more light. Okay, that's going to first order, exactly cancel the energy savings that we would have had. Okay, but it's not going to increase the amount of energy. It's only going to keep the energy the same. So that's already not as good as what we wanted, which is to decrease the amount of energy we were consuming. But it doesn't make it worse.
I'm sure we have other questions, but we've fallen a little behind, and so I think we'll move on to the next topic. Thanks again, Jeff.
Thanks, Jared.